Hello. So this is the first lecture in Physics 220. Um, in this lecture, we will be covering part of the first chapter in this course, and that's about oscillatory motion. So before I talk about oscillatory motion, I would like to show you other types of motion that perhaps you've encountered in previous courses or during high school. So there is this very famous free fall motion that people claim that Newton was sitting under a tree and then apple fell from the tree, and then he came up with all these formulas that cover Newtonian's motion. So this is a free fall motion. Another very famous motion type is the projectile motion. We see it over here with the ball play with a boy playing with this game. It looks like a ball to me. We see it when dolphins are jumping. We see it when a football player shoots a ball. We see it when basketball player shoots a ball. So all these types of motion is called projectile motion. It's motion in 2 dimensions. A third type of motion is circular motion, and it's very famous in the motion of planets around the sun. Okay, and a fourth type of motion, and that's the subject of our chapter. It's oscillatory motion, where there is, for example, a pendulum. In particular, we'll be talking about these two systems: a pendulum, where there is a rope and an object attached to its end. And then what I do is that I shift the ball from the equilibrium position to one of the two ends, okay? And then I leave it. And then what happens is that the ball will be oscillating between these two positions, what we call maximum position. So it will be oscillating, okay? And if there is no loss of energy, if there is no friction whatsoever, no air resistance, this oscillation will continue forever, okay? And over here, we see a mass spring system. I'm sure you have seen this before, or you have played with such system before. So what happens is that I have this ball, which I compress against a spring. And then from Moore's law, the spring will exert a force on this mass, which is called a restoring force. It will push it back to its equilibrium position. But by the time it goes to the equilibrium position, it will have lots of energy. So it won't be able to stop. It will continue to go to the maximum from the other side, and then back to the equilibrium, and then back to the maximum from the negative side. And this motion, again, will continue forever if there is no loss of energy. Okay? So let's talk more about simple harmonic motion. So over here, you see just a basic drawing that shows what's happening during a simple harmonic motion. So over here, I elongated the mass. Okay, I elongated the spring with the mass attached to it. Then once I release it, the mass will go back. It will pass through this position, which we call equilibrium. Then it will compress the spring, then back to the equilibrium, then it will elongate the spring, then back to the equilibrium, that it will compress, and this will go forever. So a simple harmonic motion, which we will refer to from now on as SHM, is a periodic or repetitive, okay, motion between two maximum displacements, okay, which are the maximum elongation and the maximum compression, and passing through the equilibrium position without any loss of energy. Okay, another way to see it is over here. Let's say it starts at equilibrium. So here we're saying that the object starts at equilibrium. It will move to the maximum position, negative maximum position. Then it will go back to the equilibrium, then to the positive maximum position, then back to the equilibrium. And see over here in black, this is one complete cycle, okay? Then it starts repeating. And this is why we say it's a repetitive motion, because now it will start repeating and this will go forever. Okay, that's if there is no loss of energy. Important definitions before I move forward in discussing simple harmonic motion. We will be dealing with what is called a period. And a period is the time needed for the object to complete one full cycle. Okay, so its unit is in seconds because it is time. So it is the time needed for the object to complete one full cycle. Okay, and over here, I can give you like other examples of repetitive motion. So let's assume that I go to, that there is a bus under my house, and this bus goes to the city center and then comes back every 1 hour. Okay, so every 1 hour I see the bus under my house. Okay, this means the period is 1 hour, which is in this case 3,600 seconds. So it is the time needed for the bus to complete one full cycle, that is to go to the city center and then comes back here. The frequency is the number of cycles in 1 unit of time. And usually when we say 1 unit of time, we mean in 1 second. Okay, so it is the number of cycles in 1 unit of time or in 1 second. Now, what is the relationship between T and F? Let's assume that we have this object over here and its period is 1. Remember, the period is the time needed for the object to complete one full cycle. So if it needs 1 second to finish one cycle, okay? Then how much is the frequency? Remember, the frequency is the number of cycles in 1 second, and it needs 1 second to finish one cycle. So how much is the frequency? It is 1 hertz. The unit of frequency is hertz if the unit of the time is 1 second. Okay, is it clear? Let's take another example. So if it takes 2 seconds to finish one cycle, so the frequency will be, if it takes 2 seconds to finish one cycle, okay? So the frequency is how much? How much do I finish in 1 second? It takes 2 seconds to finish one cycle. So one cycle will take half of that amount, and that is half. Okay, so the frequency will be half. If it takes half second to finish one cycle, if it takes half second to finish one cycle, this means I can do 2 cycles in 1 second. And if it takes quarter second to finish one cycle, then I can do 4 cycles in 1 second. So what I see here is that T times F is always 1, or T equal 1 over F and F equal 1 over T. You just memorize this. So if it's difficult for you to see what I'm describing over here, you can just memorize it, that T equal 1 over F and F equal 1 over T. What matters to me is that T is in seconds and frequency is in hertz. Okay. Angular frequency or angular speed, it is also a frequency, but with a different unit. So think of this as inch and meter. Okay, these two are units of distance, but it is different units. Okay, so by definition, what is the speed? Speed is distance over time. Okay, so let's say that we are interested in the distance during one period. Okay, so this is an object that will complete one complete cycle. So one complete cycle is the period. How much is the distance during one complete cycle? So during one circular motion, how much is the distance? It is 2 pi. It is 2 pi radian. So the angular speed is the angular displacement divided by the time. So omega, we refer to it by omega, it is 2 pi divided by the period, or 2 pi times 1 over period, which is omega equal 2 pi f. So these two, you memorize them, either 2 pi over t or 2 pi f, and the unit of omega is radian per second. Okay. A last definition we will be using, it's the definition of the amplitude. Okay, so we said that the object will be oscillating between two maximum positions. One is positive, one is negative. The amplitude is this maximum displacement from the equilibrium position. Okay, we refer to it by A. If we're talking about a mass spring system. Okay, so the object will be going to plus A, and then to minus A, and then to plus A, and then to minus A forever. And if we're talking about the pendulum, we refer to it by theta maximum, because the displacement will be referring to the angle. Okay, now let's do a simple exercise over here. So a mass spring system makes 30 vibrations during 1 minute. Find T, F, and W. So we start T. So we have to remember T, it is the time needed for one complete cycle. Okay, so here there is no cycles, there is vibration. So we say 30 vibrations take 1 minute, which is 60 seconds. So how much is one vibration? One vibration will be cross multiplication, T equal 1 times 60 divided by 30, and that's 2 seconds. As for the frequency, frequency is the number of cycles in 1 second. So we say 30 vibrations take 60 seconds. What is in 1 second? Also cross multiply, we get 0.5 hertz. Or we don't have to do this. We just say frequency is 1 over T, which is 1 over 2, which happens to be 0.5 hertz. Finally, omega is 2 pi f or 2 pi over t. In both cases, we will get the same answer. So it is 2 pi times 0.5, and that's pi radian per second. Oh. Okay. Let's focus now on the position of the object in a mass spring system. So consider this mass spring system where the object has a mass m and the spring has a spring constant k. Okay, so what happens to this ball at the end of the spring? At this end, or at the maximum displacement, or at A, which is the amplitude now, you know it, the ball is at maximum position and will start moving to the left due to the tension force caused by the elongated spring. Okay, remember this tension force, which is, you know, from Hooke's law. Okay, now at equilibrium, the ball is at equilibrium at x equals 0, and it will continue moving to the left due to the high energy it has. Okay, then the ball is at x equal minus x maximum, and it will start moving to the right due to the tension force caused by the compressed spring. The force F exerted by the spring is related to, so this force, it has to do with how much is the spring compressed or stretched. So if it's, for example, at maximum stretching, then this force will be maximum. If it's at the equilibrium, then there is no force at all. Okay. If it is at minimum compression, then this force is also maximum. So this force has to do with how much is this spring compressed or stretched. Okay, so think of this as this, bring a spring and compress it as much as possible. Then you will see that the force will be so high, that is when you release it, the spring will go at a very high speed, okay? However, if you compress it just a little bit and you release it, then it will just move slowly, which means the force is less. Now, it also depends on the nature of the spring, okay? If the spring is so light, then this force is so low. However, if the spring is so, it has a very high spring constant, then also its restoring force will be so high. But you have to remember that this relationship between F and X, it's true that as X increase, F increase, but it is in opposite directions. That is, if I compress the spring that is moving the object toward the negative direction, the force will be toward the positive direction. So once I release the spring, the mass will push back toward the positive direction. And if the object is at maximum elongation over here, okay, so the X is positive, the force will be toward the other end. So the force will be pushing the ball toward the other end. So the force will be negative. So F is equal minus Kx, and this is Hooke's law, if you remember it. F is called, why is F called a restoring force? So we call F the restoring force because it always helps the object to get restored, to go back to the equilibrium position. That's its job. Now, let's apply Newton's second law. So F is equal minus Kx, but we know from Newton's second law that F, the tension force, or F, is equal ma. Over here, it is the summation of forces equal to ma, but on the x-axis, there is only F. So F is also equal to ma. So minus Kx equal to ma, I get the acceleration is equal minus K over m times x. Notice that the acceleration is variable. It changes with x. If x is positive, acceleration is negative. If x is negative, acceleration is positive. So over here, when x is positive, x maximum, the acceleration is negative, and over here, the acceleration is positive. Okay, we move forward to the velocity, force, and acceleration in mass spring system. Now, let's take this very elongated position. So this is here, x equal x maximum. Okay, what happens at x equal plus x maximum? The ball is at rest over here. So over here, the ball is at rest. The spring is at maximum elongation. Implies F, which is from Hooke's law, is maximum because as x increase, F increase, but it's negative. It's negative because the x is positive, okay? And A is maximum, and it's also negative. It's also negative because x is positive. Okay, we learned this from the previous slide. We can also see that if F is negative, A is negative because this is from Newton's law. F and A are have same units, same sign. Now, what happens at x equal 0? At x equal 0 or at equilibrium, the ball is moving at maximum speed, V equal V maximum. In this case, it is negative because it's moving to the left. Okay. The spring is at equilibrium, so x is 0, right? At equilibrium, x is 0, implies F is 0, the force is 0 because force equal Kx, so the force is 0, and acceleration is 0 because acceleration is minus K over mx. So x is 0, A is 0, F is 0, okay? This happens at x equals 0. Now, what happens at x equal minus x maximum? Minus x maximum. The ball is at rest again, so the ball will compress and stops. Stops implies V is 0. The spring is at maximum compression, so the force is maximum and it's positive because it will be restoring the force in this direction, right? It will be restoring the ball in this direction, so it's positive. And A is also maximum, F is maximum, implies A is maximum, and it's positive because X is negative. And then it will get repeated, the ball is moving at maximum speed, but here maximum speed, but it's positive, V is positive because moving to the right. Okay, here we are assuming that the right direction is positive x-axis. The spring is at equilibrium, so F is 0, A is 0. And this will continue forever. Now, two important formulas I want you to memorize: V maximum and A maximum. So here we talked about A maximum and we talked about V maximum. A maximum happens at the end, at the two ends, and the V maximum happens at equilibrium. And you need to memorize that V maximum equal omega, which is angular speed or angular frequency, times A, which is the amplitude, and A maximum is omega square A. And we will see the proof for these two later on. Okay. Now let's look again. So summary of these. So if the object is moving between a plus A and minus A, here x equal plus A, here x equal minus A, here A equal minus A maximum, here A equal plus A maximum, and in the middle, A equal 0 and V equal V maximum. Okay. So if I summarize these in this table, at equilibrium, when x equals 0, V equal plus or minus V maximum, depending if it's going to the right or to the left. The force is 0 because x is 0. The acceleration is 0 because the force is 0. And the maximum displacement, at the maximum displacement plus or minus A, the object stops. So velocity is 0. The force will be plus or minus F maximum, depending if it is at plus A, F is negative. If it's at minus A, F is positive. And the acceleration is also plus or minus A maximum, also depending if it's at plus A equal minus A maximum. If it's at minus A equal plus A maximum. Let's analyze the mass spring system. So again, look at the system over here and let's take it at any position X. So what is a Newton's second law? Newton's second law say that the F net is equal ma, and here the only force along the x-axis where the movement is happening is this F of the spring, which is F. It's equal minus kx, Hooke's law. This is equal ma, and A is d2x by dt squared. This you have to remember from previous. The acceleration is the second derivative of the x, okay? So the velocity is dx by dt, and the acceleration is d2x by dt squared. So I have minus kx equal mx double prime, or x double prime equal minus k over mx. Let's take that omega is square root of k over m. So now I have this formula, x double prime equal minus omega square x. This is a second order differential equation. The solution of this differential equation is a function whose second order derivative is the same of the original multiplied by minus omega square. And this is the solution to this formula is known. It is very known. It's a cosine or a sine function that looks like this. Okay, so this is the formula, x double prime equal minus omega squared x. This is the differential equation. The solution is x of t is equal a, which is some maximum value, times cosine omega t plus phi, or x of t equal a sine omega t plus phi. You don't have to memorize both. You can stick to one of them. Let's stick to a cosine omega t plus phi, where x of t is the position of the block at any time t, a is the amplitude in meter, omega is a square root k over m, and it is, remember, this is what we got as the angular frequency, radian per second the unit. Phi is the phase constant. We call it phase constant or initial phase angle. The unit of it is radian, and we determine a and phi from the initial condition. So the question will tell me at t is 0 and v at t is 0, this is the x, this is the v. Then I can determine what is the A and what is the phi. Okay, so here you have to, so for this mass spring system, to find what is the x at any time, we have to apply this formula, x of t equal A cosine omega t plus phi. Let's see if this is correct. So if x of t equal a cosine omega t plus phi, then what is v of t? V of t is dx by dt, which is the derivative of this. The derivative of cosine is minus sine, and here the omega will jump outside. So this will be minus A omega sine omega t plus phi. And this is minus, okay, what is omega A over here? Omega A over here is V maximum, remember? So V of t is equal minus V maximum sine omega t plus phi implies V maximum equal omega A. This is what we said, we will prove it later. So V maximum is equal, so here you can see that V maximum is omega A. Now, A of t is d2x by dt square or dv by dt. So again, I have to do the derivative of this equation. So the omega will jump outside and the derivative of sine is cosine. So I have minus A omega square cosine omega t plus phi. What is A cosine omega t plus phi? Here it is. A cosine omega t plus phi is x of t. So it is minus omega square x of t. And whatever is outside the cosine function is A maximum. So A maximum is A omega square. Okay. Note that from up there, we said that omega is square root k over m, right? So this is equal to pi over t. So the period t is 2 pi square root m over k, and f is 1 over 2 pi square root k over m. This comes either from omega over 2 pi or from 1 over t. So the period is 2 pi radical or square root m over k, and f is 1 over 2 pi square root k over m. Now, what happens as the mass increase? As the mass increase, t increase, but as the mass increase, f decrease. F and omega are directly proportional. So if f decrease, omega decrease. Okay, then what happens if k increase? If k increase, the period decrease. However, the frequency increase and the omega increase. Okay, let's do one exercise from your booklet. This is number 15. Just a second. Okay. So a particle moving along the x-axis in simple harmonic motion starts from its equilibrium position. So here we know that at t equals 0, x equals 0. Okay, the origin at equilibrium position, the origin. And it's moving to the right. Moving to the right implies V is positive. So at t equals 0, V is positive because it's moving to the right. The amplitude of its motion, A, is 2 centimeters. We can directly make it 0.02 meters so as we don't get lost later. And the frequency is 1.5 hertz. Okay. There is no harm in calculating the time over here. So this is 0.66. So it's 1 over frequency, and this is 0.666 seconds. Okay, find an expression for the position of the particle as a function of time. Here we directly say x is equal A cosine omega, or let's say W t plus phi. Okay, so what is omega? Omega we know. Omega is 2 pi f, and this is equal 2 times 3.4, or 2 pi times f is 1.5, so this is the 3 pi. We can keep it like this. We can keep it in pi. Okay, so this is omega. Now we need the amplitude. Amplitude is given 0.02 meter, and we need phi. To find phi, we use at t equals 0, x equals 0, which is equal to, if we use this formula, so at t equals 0, x is equal A cosine omega t, instead of t, I will put 0, so A cosine phi. And this is equal to 0, implies how much should phi be? So this is A here, 0.02. So how much should phi be in order to get cosine phi is 0? So phi should be plus or minus pi over 2, right? Because cosine phi over 2 is 0. Now, which one should we take, plus or minus? To know, we will use at t equals 0, v is positive, right? But v, what does it equal? V is equal minus 0.02 times 3 pi, right? Times sine omega t, which is 0, plus phi, okay? And in this case, so I have a minus sign here. What should phi be so as v will be positive? Let's say phi is pi over 2. Sine pi over 2 is 1. So the velocity will be negative at t equals 0. But I want it to be positive, so implies phi will be minus pi over 2. So I get the equation x equal 0.02 cosine instead of omega 3 pi t minus pi over 2. Okay, so that's part A. Part B, determine the maximum speed of the particle. Maximum speed is V maximum. This is equal omega times A, which is equal omega 3 pi times the amplitude 0.02. And this will give me 0.1885 meters per second. Okay, so find the speed of the particle and the earliest time at which the particle has its speed. So remember that the object was at equilibrium. Okay, and it moved from it's moving between the maximum and back, sorry. It's moving between the maximum and the minimum. Sorry, I'm not very good in drawing. So it was here, okay? Now it will go to the maximum, then it will go here to the equilibrium. So determine the earliest time at which the particle has its speed. So the earliest time is it will go to the maximum. This will take t over 4. Then it will go back to equilibrium. And that's where it has the V maximum again. So it will have maximum speed again when it passes through the equilibrium on its way back from the maximum position. Okay, this needs t over 4 times 2, and this is equal t over 2, which is 0.333 seconds. Okay, now find the maximum positive acceleration and the earliest time at which the particle has this acceleration. So find find the maximum positive acceleration. So we have to apply actually so let's see the solution. So the maximum positive acceleration, this is part C. A maximum is omega square A. So instead of A is 0.02 times 3 pi squared. So this is the value. And I need to determine, according to the question, the earliest time at which the particle has this acceleration. Okay, so the earliest time at which the particle has this acceleration. So remember that now the object which is at the origin will go to the, we need the maximum positive acceleration. So when does the object has positive maximum acceleration? It has it here at minus a, remember? So at the plus a, the acceleration is maximum, but it's negative. And at minus a, the acceleration is maximum and it's positive. So when does it have the maximum positive acceleration? When it goes to plus a, back to the equilibrium, back to minus a, that's when it has maximum positive acceleration. So how long does it take to reach this position? Look, it takes t over 4, t over 4, t over 4. Okay, so all this before it completes its cycle and goes back to equilibrium. So it takes a 3 over 4 period, because it takes 1 t over 4, 2 t over 4, 3 over 4. And instead of period, I'll put 0.66, and this will give me 0.5 seconds. Finally, find the total distance traveled by the particle between t equals 0 and t equal 1 second. Okay, so here I will say t equal 1 second. This is equal with respect to the period. So the period t is 0.666 seconds. Okay, 1 second equal how much? This will be 1.5 the period. So let's do it in another way. So the one period is 0.66 seconds. How much is 1.5 seconds? And here, if I do cross multiply, I will get that the time is 1.5 period. Okay. Now, I know that in one period, the object will go from 0 to plus a to a, back to 0, back to minus a, back to 0. So it's from 0 to a, from a to 0, from 0 to minus a, from a to 0. So how much is this distance? How much? I know that from 0 to a, it is 2 centimeters. So from here to here, 2 centimeters, from here to here, 2 centimeters, 2 centimeters, 2 centimeters. So this gives me 8 centimeters. This is in one period. So in half period, how much? So in the additional half period, it will go from 0 to a and back to 0. So this is another 4 centimeters. So in total, the object will move a distance of 12 centimeters. Oh. So that's it for today. In the next lecture, I will solve more exercises on these formulas, so as we understand them better. And if you have any questions, please send me an email so as I can cover it during the live session on Thursday. We will have our first live session on Thursday. That's it for today. Bye-bye.